All right, good afternoon. Let's get started. Any questions before we get started? Let me just make sure I decided to record to the laptop and I'll post things on YouTube. I never did get those other videos. So we're continuing our discussion on gain bandwidth. And this is a Bode plot of an op amp, right? And I'm just going to flip it upside down. And this is the AC analysis. And we can see that the phase is 0 for 1 hertz and presumably below. And assuming this doesn't dip, right, 1 hertz, we're kind of calling close to DC. And so the open loop gain would be ten to the 56 divided by 20. Which is which is 630. All right, and we'll get into that later. So in order to find the gain bandwidth, we just find where the magnitude equals 0 dB or V out equals V in. So all you have to do is draw a relatively straight line, hit the magnitude, all right, and that's 2 megahertz. All right, which you would get from the data sheet. It would just give you, it's really giving you this point, right? And it gives it to you as the gain bandwidth. And then it really gives you this number here at DC. It doesn't really tell you this pole. All right. And so if I actually wanted to draw this transfer function, and let's just say if I took the phase and did that, and we're ignoring this right now, right? I would have h of s equals 630, which I just read off of that, times s plus 2 pi 2 kilohertz. And if we set s equal to 0, then you'd get 630 divided by this. So this is omega naught, and then you have to put it up here. All right. So that would be the transfer function. So usually the first problem is just identifying the gain bandwidth and the open loop gain. And like I said before, this spot, yeah, it'll be given in Ltspice, but not really on the data sheet. And so, right, the big idea is that the magnitude of whatever transfer function you're trying to create just has to be below that line. Okay. Any questions so far? Oh, I just okay. So I don't know what happened to the last lecture. It never came. Maybe I recorded it to my computer, and I'll have to see if I can find it. But I do believe on that particular module, I've got older videos that you can see. And then I'm talking about the range that the op-amp functions normally. Yeah, I mean, I'm basically today's topic really just going over homework problems. And so yeah, and so yeah, no, I want to post it. I didn't go into work today to see if I could find it on my machine. What do I call this? What would I call this? I mean, I guess this whole topic is gain bandwidth, right? And I'm just trying to show you what the data sheet is, right? And this would be the open loop gain, right? So if I say, here's a Bodie plot, tell me the open loop gain, right? And then either identify or what does the gain bandwidth mean? That's this spot, right? So call it gain bandwidth, AVOL, and we're doing it graphically, yeah, on a Bodie plot. Okay. Okay. Yeah, for some reason, when somebody has a message, I don't get a ping or anything. But you might not see my messages, but it's like blocking up a lot of the screen. That's why I'm putting it kind of out of the way. So if I'm like really ignoring you for a long time, just email me, and I'm setting the ringer on my phone to loud, and then I'll know. All right. Okay. But if I ask a question, yeah, it might be better than to unmute your microphone and then ask it. That way I'll know. So But if we look at homework 8, this is a realistic Bode plot, right? And I'm just asking you to estimate the gain bandwidth and the DC gain. So that's basically question 1, right? Question 2, we're getting into what's going on, right? When is it ideal? When is it a finite but constant? When is it like a low pass? And when does it look like an integrator? So this is the same Bode plot. And we have a few questions. So when does it behave like an ideal op amp? Well, basically an ideal op amp, the transfer function of the op amp would just be infinity, right? Well, all of these are finite numbers, and so nowhere. That's easy. Then the next one is, and I'm going to use the equations like HS equals open loop gain. That's a constant and it has no frequency response. So where is it doing that? Well, actually, right here. There's pretty much no frequency response in that range. All right. Now, where is it acting like an integrator? Well, if you have a constant divided by S, that's an integrator. And we can see that in this range, the phase is very close to minus 90, right? Because that's J omega, which is omega with a phase of 90, but it's in the denominator, so the phase turns negative when we bring it up into the numerator, right? So in fact, now the phase does start to dip in here. There's more going on in this op amp. So really, like between here and here, it's acting like an ideal integrator. Now then what about the low pass filter, right? Well, low pass has some kind of cutoff frequency, S plus omega naught, and it can have some kind of gain, right? Well, here's the gain, right? And then here's the low pass, right? And so in this region, it's really acting like a low pass, which I would just say and since I can see where that pole is, I can write out the transfer function kind of exactly. All right. So those are the main regions where this is acting, like the various op amp models, which can help you debug what's going on when you're pushing the limits of an op amp. So that was basically, if you know, the topic of this slide is, oops, question 2 from the homework, right? And it's just the model range of each one. Okay, any questions? All right, now this is the op amp in Ltspice if I simulate it out even farther. Okay, I'm actually simulating it out to a gigahertz. And so where this could be trouble is, let's do HS equals 100 hertz times 2 pi divided by S. So because this scale is comes out in frequency, so we'll say 100. So when we're at 100 hertz, okay, we should be at 0 dB. And then to try to, so that's a decade over, and that's 20 up. Okay, and I'm just going to try to draw this line. It's not very straight, but we can see that it intersects up here, so it'll stop working. All right, but also it intersects down here, and so it stops working. Now, what if we took a different point, kilohertz, right? So 1K 2 pi divided by S. Well, the line will be in parallel with the previous integrator, as much as my shaky hand can do. And you can see that the frequency range has been reduced even more. And let's just go to 100K. And you can see that the frequency range is even reduced more. And so without seeing the whole transfer function, you'd never see these points down here that it's where it's integrating. I mean, intersecting, right? This you can easily do the low frequency end, but the high frequency ends have an impact as well. All right. And this turned out to be really important in my research because I had an op amp that I had designed, and just let me recalculate what its So I'd actually had an op amp designed kind of very similar specs, but the trick is that I couldn't make the integrator too fast, or it would kind of stop working at DC for me. All right. Sorry, I just needed. All right. All right. So this is a non-inverting gain stage, which we would call our HS desired is 1 plus R over 2, right? That's if the op amp is behaving ideally. Well, now you don't just assume it, the range. All right. So if I have R1 equals 0, no, if R1 equals infinity and R2 equals 0, right, the gain equals 1 equals 0 dB. So graphically, I just draw right out to the gain bandwidth limit. All right. And so between there and there is where it'll be mostly ideal. Now, really, it's somewhere before that. Okay. Well, I'm not going to get into the R2 and R, but if the gain were 10, right, that's 20 dB. And now you can see that frequency range is reduced. And when you're doing the homework, you can just bring it right here to the edge. That's fine, right? And if the gain, oops. 40 dB. Okay. And gain 1K, 60 dB. Well, this line is below 60 dB, and so there's nowhere that it's going to work. All right. Now, this analysis, this graphical analysis, it can work for the inverting stage as well. Okay. And the magnitudes would still be, so if you had a gain of -1, you'd still have 0 dB. -10, 20 dB, right? The phase would be different. But in practice, though, it rolls off more before you get there. But really, it's a good estimate that you can use. Say graphically, where would this behave as a gain stage? All right. Now, you might see a question. Like this. All right, and we have, if that op amp is ideal, we have something like that, right? And we can have there is no gain because of that buffer, right? So I can have a low pass filter and I can have a cutoff there. I can have cutoff here, still work, cutoff here, it'll still work, right? But if I try to have my cutoff frequency out here beyond that limit, well, no, that's not going to work, all right? Now, so let's go into a little more detail. The transfer function I want let's say is this, all right? And I'm achieving it like this. Where will this circuit work, right? Well, this is V plus, right? And this is V minus. And yeah, if these were ideal parts, this would work over every frequency range because it is what it is. But this has a gain bandwidth limitation, right? We're not quite sure what it looks like. but we really have to be below that line. And so I can, like I said, I can have a low pass, low pass, low pass, low pass. Not really, even if it lines up, because this line moves around too much, right? So you just have to have that low pass below. So the thing is where, the question isn't so much where is this right, is where will this act like a buffer? That's the true question. So you have to know the model, right? So we have HS, and we'll call it the buffer, would be the HS of the op amp, right? 1 plus HS of the op amp times the feedback. All right. Now we've done this before, but we'll just have a quick review. And I'm just going to put this upside down. All right. That's the summer. Here's my output. It's scaled by G and subtracted. All right. That means, and this is in. So V out equals V in straight through the summer, right? But then it's also subtracted V out G. Oh, I'm sorry. There's an HS in here.
What does a buffer do again?
It isolates this node from that node. All right. So let's say I'm driving a load, right? I can design my filter over here. All right. And then this voltage becomes that voltage, and it drives whatever I need to drive there. No problem. If I didn't do that, I would have this. Which totally changes where the cutoff frequency would happen. And every time I change this load, my cutoff frequency would change as well. So you're really just isolating one thing. You're buffering it. You're isolating one node from another so that you don't, things don't interact. Does that answer your question?
Yeah, I think so. I can't see exactly what you drew there at the bottom. If you could just scroll down a little bit.
What's in the way?
The toolbar. There. Yeah, okay, I was just ground. All right, sorry. Yeah. Thanks. Yeah, that makes sense.
Okay. Yeah, that's nice to validate that question. Okay. I know it can be tough, especially because you kind of have to interrupt, if you will. But again, I don't take it that way. And they tell me I need 2 computer screens, and then I could have one screen for monitoring and one for drawing. Okay. So fortunately, oops, there should have been an HS box here. So then V out equals V in HS of the op amp, right? The internal part, minus G HS V out. And then when I solve for V out over V in, that's where I get my HS 1 plus G HS. All right. And in this case, because the buffer is V out equals V in, G is 1. So I'm left, and now I'm going to draw your attention. I'm going to start drawing it over here. So G equals 1, and then it depends on the model. I think I'm going to add another, I'm going to move to another layer. Okay. So HS equals infinity, HS, I'm going to call it B for buffer and probably stop writing it. So then I have infinity 1 plus G times infinity, and infinity is 1. Well, then input equals output for all frequencies. All right. Now, if HS of that particular op amp is some finite number, then HS of the buffer equals all right, and that's 1. So really, to get these two to cancel out, that transfer ratio times the open loop gain just has to be a lot bigger than 1. And then it'll be ideal, and then it'll be like a buffer. Now, what about the integrator case? All right. Okay, so I'm going to multiply through by S. All right. Well, when will these open loop gains cancel out? Well, when when the open loop gain, so omega has to be less than this ratio times the open loop gain. And that G is not, it's the voltage division. So the closer to 1 this is, the closer G is to 1, the more it's like a buffer. The smaller G is, the more gain you have, which is so this is my AV over S, right? G equaling 1, right? That's the biggest thing. So the range of omega is large. But when G is less than 1, the gain is higher and it reduces the range. Okay, and you get that as the gain is increasing or the transfer ratio is decreasing, you're moving up that way. All right, any questions on that so far? So there's many questions, right, that I'll ask you kind of graphically, where will it work? But then no, find an actual number, where will it work? All right. Now, all right, I guess I am doing, I thought I was doing sample problems. Because in the problems, I don't necessarily give you a number for open loop gain. I'm telling you to find these relationships, okay? So, not that I'm not open to it, I just not quite sure. Sorry, I'm trying to find. No, that's not it. So, I mean, this is homework 8, right? I kind of said, where is it? And I just did it on the graph. What are the frequency ranges, right? It's the same questions. I just did it for a different plot. Here I did gain 1, 10, and 1,000, but a different op amp structure. Kind of did this one. Okay. And just did this one, but we didn't do this bit right here. And the only, yeah, we just didn't, I was about to do this part. Okay. I'm not trying to embarrass anybody. I just don't know what you mean. Op amp diagram. I'm sorry, Mike. I don't know what that means. An op
Is
amp.
there an example? Is that made with an RLC circuit, or is there an example where you can show that how you get that equation using op amps and the resistor and the capacitor, like the different filters that are that go into designing that?
Oh, do you mean design a circuit that does that?
Yes, exactly.
Okay. All right. I guess I hadn't done that because it isn't part of this homework set, but it is a pretty good question. All right. So what I can do graphically, right, is say, or even let's give it a gain, right? So that's 20 dB, right? And this is going to be, the way I've drawn it is 1 kilohertz. All right. So then um, yeah, there's we have an RC filter. And since we're talking about op amps, yeah, you really do need that buffer, right? But also we need an op amp, oops, because we need gain. Okay. So I break the problem up and say, here is my from here, I'm going to get 1 over RC and then I have to choose right, because that's the frequency. I need to multiply it by 2 pi to get radians. And I could say, all right, C equals 1 nanofarad, and then calculate R to get some value, right? That's one way, right? Another way, and which I would say for a single pole filter, I would say is really the way to do it, because the other method to use an op amp would be DF2 okay. So I have 1, 2 inputs here. I have no inputs. So I can put 2 dummy resistors to balance it. The problem is this is coming out inverting. So I need to uninvert it. And yeah, sure, I could use 10K here, but I'm already up to 3 op amps, right? Not really worth it. Okay. And yeah, I guess you could use an RL circuit as well. But in general, for first order, that's all you would do. All right. Now, hey, here's an RLC. I would say go, the homework solutions will be published tomorrow, but those were other days where I actually said, here's how to calculate the values for that, okay? But now, that's the R and the C part. Now what about the op amp part? Well, if I were to have to look at a data sheet, right, I have 20 dB. Well, I mean, I need my open loop gain to be greater than, much greater than 20 dB. So that could be, you know, just find something with an open loop gain on the data sheet that just said greater than 60 dB. Now here, and then I have to make sure that it's less than the gain bandwidth, right? So if I'm 20 dB here, right, and I go another decade, I will go down to 0 dB, right? So at 10 kilohertz, I'm 0 dB. That means the gain bandwidth should be bigger than 10 kilohertz. And then you could just find an op amp that did it. But in general, the op amps it's hard to find one with a gain bandwidth of less than a megahertz. But that's how you would go about it. Of course, the other way to go about it so I posted a FAQ today, and in that FAQ, there's this wizard. And yeah, you just say, well, here's my filter that I want. And you can, there's more things that we haven't gone over yet, right? And if you just keep, I want to compensate for gain bandwidth and I want low power, you can see it's coming up with the numbers and the architect, the op amp for you, right? So it's taking care of that. And then it's even giving you a parts list. You can get even a, before the Spice, it didn't seem to work that well, but yeah, when you run it, it doesn't give you a nice diagram in Ltspice, but it will run. So that would be your design filter. But the Spice deck is all text, not done graphically. All right. So that is like, you know, another way to do it. Of course, you kind of have to know what you're doing to make use of that filter.
That I do not.
Hold on a second. Okay. So did that answer your question?
Yes, absolutely. Thank you.
Okay. Now that was a lot of information in a real short time, and so it's a very deep question as well, and it's in DF2 FAQ where I'm going over the major architectures, and I don't necessarily tell you how to solve it here, but I'm giving you the big idea of what's going on. Okay. Sorry, I'm just trying to. Yeah, my toolbar is acting a little strangely. So I didn't do this kind of problem yet. Which is right, conveniently located right here. So you can see that that simple model, right, isn't, all right, no, that's the filter. This is straight op amp, right? Oh, up until here, it's like a first order filter. And then we have another break frequency, but the phase goes down. There's a lot going on here at the upper frequencies that I don't want to explain today. And when you actually learn how to design op amps in 124, you get more into that. All right. But even with you use a second order model, oops, I want to be invisible. Okay. So here's the thing, right? This is a buffer, right? If I put in a step, I should get out a step. But you can actually get ringing. And it's all based on this and the fact that while we might use the open loop gain is infinite, finite, integrator, first order, it's really none of those, right? It's something much more complicated. But even with two poles, you can get ringing. But look, let's just have a quick review, right? This is a real number, completely real. This is completely real. So if I were to try to plot these on the S-plane, I'd have one at 1 and then another one at a gig. All right. So that's underdamped, right? So the op amp itself is underdamped, right? That means, and it's like a low pass. So it comes out, I have a break at 1, and then I'll have another break at 1 gig, right? You can see these two separate breakpoints, and so there's not going to be any ringing. Well, let's put it in the feedback. Now I'm going to say HS of the op amp, right, is 100K times 1 gig. I break it up like that so I can keep track of what I'm doing, because at DC, the 1 gigs cancel out, and then I'm left with an open loop gain of 100K. S plus 1, S plus 1G. Now, if we take our kind of generic buffer equation, that G transfer ratio is 1. And so HS of the buffer is really HS op amp 1 plus HS op amp. And I have a lot of things, I might call them old homeworks, or I might call them case studies where I've done it out. So you should be able to, like a textbook, be able to read them and go forward. So here I just have 100K times 1G, S plus 1, S plus 1G. Then I multiply, oops, sorry, 1 plus, I'm not going to draw it out again, HS. And it gets a little bit messy. Here's my 100K times 1G. These real poles get multiplied by 1, and so they're there. All right. And then these, because HS, right, is this divided by that. Well, these real poles cancel out, and so I'm really left with the numerator. All right. And now it's not the same anymore. It's not, I might not have, oh, you're saying it's hard to see up there. So you multiply, and so now I'm just going to look at the denominator. All right, I'm going to multiply it out. S squared plus 1g. And then just so you don't think I'm forgetting anything, I'm just going to add 1 to 1g. But of course, it's effectively that, right? And so now that's my C, that's my B, and A is 1. And I can just, I don't need the whole quadratic equation, I just need this bit, right? And if B squared is greater than 4AC over, if it's equal to that, critical. Less than, underdamped, which is ringing. Ringing is a fancy term for a signal that's turning on and then doesn't settle right away. It rings as it goes. All right. So really, we're looking at 1g squared versus 4 times 100k times 1g. Well, this is 1g times 1g. This is something less than 1g times less g. So in fact, it's still going to be overdamped, so it won't ring on us. But sometimes I set it so that the question, it comes up that it rings. All right. So that's a pretty classic exam question. Oops. Okay, so this is a buffer, right? V out should always equal to BV in. We should always have well, so what I'm saying is that this line should be 0 for infinity. So where is the gain bandwidth having an effect? Well, it's actually, the phase starts deviating from 0 about here, but really we can see that this is, that it's actually, that feedback network is actually causing a peak here, which means there's a complex pole. Then it comes down, and it's coming back up. So that's kind of pretty wild. It's not working there, right? So all you would have to do is circle where it's kind of deviating, right? Now, there's other things as well. So I have a high pass filter. Actually, right, this is a high pass filter. And I'm gonna label that node 1. Then you can, or I is fine. Okay. So this looks like a high pass filter until it doesn't. What would the ideal high pass filter look like? Right there. So there's the ideal, there's the buffer, and it deviates right from there, and you would just circle it. Now I know in lab, let's see, we're set for time. Yeah, in lab, you can use a behavioral source. Let's see. Oh, hey, it looks like my internet connection is unstable. Sorry. I just must have typed it in wrong. Oh, I did. Okay. So VCheck, that's the perfect high pass filter response. So was VI, and you can see that it's deviating right here. You can just draw a circle. We have a few more moments. Are there any questions? Okay. Well, I guess that's it. I'm going to make a post, but like from an admin point of view, I want to talk about exams, right? And yeah, everything's going to have to be online. If you go through the AEC, don't worry about it. I can see what your times are, right? And custom make your exam, all right? Let's see. It's at the very least, right? The exams, different people will get different, let's say, kinds of, not, the questions will be the same, but at least the numbers would be different. The exams would come off the homework anyway, and you either type your answer in, right? Even if it looks like, rotten computer code, I can answer it. And then you would basically take a picture.
Professor?
Oh, yes, sir. Oh, 4. Oh, wow.
You've been cutting out for the past minute.
I got a message. Yeah. All right. You know what? Um, Sorry, it's more like a code. All right, just don't worry about the AC. I can program different times. Okay, so it's yeah, so the video is recording, so I'll post it and then you should be able to get it. But basically you would enter your answers into Canvas, and then you would take a pic of your work and submit that as a different assignment. And then that's not really graded, right? That's just there to make sure. I'm right now exploring, the Respondus lockdown browser and things like that. But I'm only, it's probably time, it's time to go if internet bad, at least. Okay. So if anybody has a question they want to type in the chat, maybe I can answer it for the video, right? And then you can see it later. Okay. Okay, so anyway, you guys had some really deep questions today, and I really appreciate that. And okay, academic holds. I just happen to know that you can make online appointments with Zoom, which somebody already said. Okay. Anyway, I think we'll end it here, and then you can just email me. All right, so thanks for coming. Take care. Bye.
Thanks, Professor. Thanks.
Oh, thank you.